My name is Charles Vincent Terenal, and I'm from DC Pet 31. In this reflection, I'll want to take a look at how GPUs evolved, why they became the backbone of modern AI, and where technologies like digital twins, autonomous vehicles, and the metaverse are heading. After watching the three videos, it became clear that we're living in a transition period. The hardware, the software, and the expectations of society are all changing at the same time. As future engineers, we need to understand what those changes actually mean. The first video focused on the growth of CPUs, and one thing stood out immediately. The scale of change is not linear. What do I mean by this? It's exponential. The early generations of GPUs had only a small number of cores, originally built for basic graphics. But once the industry pushed for realism in gaming, better lighting, reflections, physics, textures, the GPU had to become massively parallel. That pressure from gaming unintentionally created the perfect hardware for AI. Deep learning depends on repeated matrix operations. GPUs were already optimized for repetitive math because rendering graphics is basically the same thing. That's why AI engineers moved from CPUs to GPUs. It was not a small jump. It was 10 times, 50 times, or even 100 times the performance jump from CPUs to GPUs. The video also showed how companies like NVIDIA redesigned their hardware around machine learning. Tensor cores, for example, were created specifically for matrix multiplication at high speed. A GPU that was rated at a certain number of teraflops suddenly delivered 8 times more the performance on AI workloads. That shift didn't happen by accident. It was a deliberate move because AI became the new frontier. What also stood out was the ecosystem. It's not just the raw chip, it's the memory bandwidth that interconnects the compilers, the optimization software, and even the cooling systems. AI hardware is now treated like an industrial infrastructure. Data centers are being built around GPUs, and the industry is accelerating because of every new breakthrough reinforces the need for even more powerful hardware, to be more specific, GPUs. And this just made me realize that GPUs are no longer about graphics like before. They're becoming the new general purpose engine of modern computation. If CPUs define the last few decades, GPUs will define the next ones. The second video focused on intelligent vehicles, and it showed how GPUs are now at the center of autonomous driving. Cars are becoming computers that happen to have wheels. They have multiple sensors, cameras, radars, ultrasonics, and sometimes even LiDAR. All that data has to be processed in real time, and only GPUs can keep up with that volume. The interesting part was seeing how these systems build a 4D environment map. That's not just adding depth, it's predicting how objects will move over time. The AI has to decide when to brake, when to accelerate, when to turn, and how to react to unpredictable situations. It's not enough for the car just to see, it also has to understand. The video also touched on how companies use massive simulation environments. Instead of waiting for millions of real-world miles, they use GPU accelerated simulators to test every scenario. Weather, lightning, traffic patterns, rare edge cases. And the more the AI learns, the better the real-world performance becomes. What this tells me is that autonomous driving is not just about sensors. It's about compute. A modern autonomous vehicle needs the equivalent of a small data center inside it. That's the level of demand we're dealing with. As future engineers, this trend affects us directly. Whether we go to networking, hardware engineering, or software, the systems we build will eventually interact with machines that rely on real-time AI. That changes the expectations of reliability, latency, and safety. We're no longer just writing code or designing circuits. We're contributing to systems that make real-world decisions. The third video talked about future technologies and questioned which ones are real and which ones are just hype. It covered blockchain, cryptocurrencies, AI tools, automation, and other emerging tech. And the message was very straightforward. Technology only becomes real when it solves a real problem and it becomes a part of daily life. Let's take a look at blockchain. It's a very good example. The ideas behind it, decentralization, transparency, and security, they're all valuable. But the majority of crypto projects became hype because they didn't offer real utility. AI tools, on the other hand, did not need hype at all. They became mainstream because they solved the real-world problems immediately. And the lesson here is fairly simple. The future will be shaped by technologies that deliver real-world results, not just buzzwords. We have to be critical, not gullible. We have to understand the logic behind the tech instead of trusting trends. Many emerging technologies fail because they chase attention instead of impact. As engineers, we're going to encounter this very frequently. We will see a lot of projects that are exciting, but in the end pointless and have no real direction. We will see others that look boring on the other hand, but become essential. Part of our job is to understand which is which. And digital twins were one of the interesting topics presented across the videos. They create real-time digital copies of physical environments, and these models allow engineers to test upgrades, simulate failures, optimize routes, and plan infrastructure without disrupting our real world. It's like having another world, but virtually. If GPUs drove the rise of AI, they will also drive the rise of digital twins. The amount of computation needed to simulate real-world physics, material behavior, environmental data, and system interactions is massive. Only GPU clusters can handle that scale. Digital twins also connect directly to the metaverse concept, not the hype version where people buy virtual land, virtual items. I'm talking about the industrial metaverse, where simulation guide real construction, where robots can rehearse tasks, and where projects can be validated before physical execution. This is where I see the most practical future, not VR games, but fully simulated environments that feed real operations. Companies like BMW, Amazon, Boeing are already using digital twins with GPU accelerated environments. This is not hype. This is happening now. Based on all the three videos, GPU development is moving in three directions. 1. More parallelism. We're going to see more GPUs with tens of thousands of cores. The math operations behind AI aren't slowing down, so the hardware definitely won't either. 2. We'll see more specialized hardware, tensor cores, ray tracing cores, and future AI optimized units will continue to be developed. GPUs will not become general purpose anymore. They may become specialized for AI, robotics, graphics, and simulation. The third and last is larger scale systems. The biggest breakthroughs won't come from a single GPU, they'll come from thousands of GPUs working together through fast interconnects, clusters. Supercomputers, autonomous vehicles, smart cities, robotic fleets. These systems will depend on distributed GPU computing, not just single GPU, but clusters, hundreds and thousands. This aligns with the trends we're already seeing in cloud services and edge computing. AI is moving closer and closer to the user. GPUs are following. The main realization for me as a future engineer is that we won't be becoming a part of a generation of engineers who won't just use technology. We will shape how society interacts with it. Here are the responsibilities I took away from the videos. We need to understand AI fundamentals. It doesn't matter if you specialize in networking, hardware, or software. AI will merge with all of these industries. So we have to understand how the nuances work. We need to respect the scale of modern computing. Data centers, autonomous vehicles, and digital twins, they all require massive compute. That changes how we design infrastructure. We also need to stay critical. A lot of technologies are exciting, but some have no value and are only there for the hype and probably money making purposes. We have to distinguish real innovation from the hype. We also need to consider the ethics and long term impact. The systems we will build will influence safety, privacy, employment, and social behavior. We cannot ignore these consequences. And of course, we need to be adaptable. Technology changes fast. Engineers who stop learning will obviously fall behind. To conclude, these three videos made one thing clear. GPUs have transformed from gaming hardware into the foundation of AI. And now they're pushing the next wave of innovation. Autonomous vehicles, robotics, large-scale simulations, and digital twins. As future engineers, we are entering a world where computation, intelligence, and real-world systems are merging. The future isn't just software or hardware anymore. It's the integration of both, accelerated by GPUs and driven by AI. And that direction is unavoidable, honestly. More intelligent systems, realistic simulations, more automation, and deeper reliance on high performance computing. This is just how it is. And our role is to make sure we understand these changes, use them responsibly, and prepare ourselves for a future where engineering decisions will shape how society moves forward. That's all from me. Thank you very much.